Hello everyone, welcome back to another video lecture from Miss Simoneau. This evening we're going to be talking about radiant energy, and this is chapter 4 in your textbook, and you can see the pages that you might want to read if you're feeling like a little confused. When we discuss light, we say that light has a dual nature. And we say it has a dual nature because light can be described as a wave, but it also can be described as a particle. So over the next few slides, we're going to go ahead and discuss this. Also, I'm sorry, I know you can't see this video. We'll try to watch this one in class. So let's first start off by talking about light as it behaves like a wave. So first off, we should know that light is a type of electromagnetic radiation, and there are many other types of electromagnetic radiation, and we'll see a picture of that in a minute. But for example, gamma rays, radio waves, X-rays, these are all things that are electromagnetic radiation, and notice I use the word wave in all of those. So even though we say light, light really has a specific wave associated with it. So as you can see kind of here in the picture here, I have this wave here. And so a couple of things. So amplitude, so some terms you need to know about waves. Amplitude is basically the height that is the wave is from the center line. Do you see this line that's like bisecting the wave? And I'm not exactly an artist, but hopefully you're getting the idea that it should be the same on the top and the bottom. Wavelength is the distance. Usually we measure it from peak to peak, or sometimes that's called crest to crest if you're thinking of a wave. Although I have to say that I've seen wavelength measured from trough to trough as well. Frequency. Now frequency, this is a little trickier. This is the number of times that a wave passes through a certain spot per second. So when we talk about the unit for frequency, it's actually 1 over s, because how many times per second does something pass through it. And I guess at this point I should mention wavelength is usually measured in meters, or we'll also see it in nanometers. And then speed. Speed is just another way that we can measure things, and the way those units for speed are in meters per second. So we can measure basically how fast or how far over a specific time the wave is traveling. So again, just a quick review. Amplitude is the height of the wave. It measures the brightness, or sometimes we'll call it the intensity of the light. And so, here's a much better drawing of the amplitude, and then you can see this thing that's like bisecting the wave here. And notice it's called a crest here. Sometimes I hear it called a peak. Wavelength is the distance between the crests, or those peaks. And for visible light, the wavelength is 400 nanometers to 750 nanometers. Violet light has a shorter wavelength. You can see it's at only 400 nanometers, while red light has a longer wavelength. And again, here's our picture of our wavelength. So when we discuss the speed of something, remember it was measured in meters per second. And so since we're talking about light, all light travels through space at 3.00 times 10 to the 8th meters per second. So that's a constant that you guys will have to remember. So again, you need to know that light travels at 3.00 times 10 to the 8th meters per second. And just so you're not like freaked out on like some other worksheets, or maybe when you get to AP chemistry, you might see that value at 2.99 times 10 to the 8th meters per second. And the reason for that is, if you remember, we talked about the value pi, how like pi is like goes on for like a really long time, but we just round it to 3.14, or we mentioned that's kind of a similar thing with moles. This is just a slightly different, I don't know if you want to call it a more precise measurement of speed, but for us, all we need to do is memorize this 3.00 times 10 to the 8th meters per second. And the last variable to talk about here is frequency. So frequency is the number of complete waves passing a fixed point in a given time. So that's a much better definition than I gave you earlier. And so when we have frequency, we can measure it by taking the speed of light over the wavelength. So how fast is it traveling divided by the wavelength. And then so if you look down here, you can see the equation that we're going to be using. Again, it's an equation that you'll need to memorize. So this term right here is standing for frequency. Okay, so this is for this one. Then we have a speed of light up here, and that's represented by the value c. And then we have a wavelength down here, which is representing this wavelength right here. So again, if we were talking about the units that we might see, remember that speed of light is meters per second. Wavelength is in meters, and then frequency is 1 over s. So hopefully you can kind of see how those units are canceling out there. So we have this little picture over here of these different colored waves. So if we were looking at this first one here, I'm hoping that you would say, oh, well, this one has the longest wavelength, and that's because it has the longest distance between peak to peak. Then this is the next wavelength, and then this one down here, which I don't know if you guys can see, this purple one definitely has the shortest wavelength. And so if we're looking at that as a factor, are you guys noticing how it's on the bottom here? So the longer the wavelength, the smaller the frequency is going to be. So when we talk about the relationship between the variables here, as this value gets bigger, this value is going to get smaller, right? Are you guys seeing how like we'll be dividing it by a bigger value? So we like to say that red light has a long wavelength, but it has a very small frequency. And you can see if I was to pass it like through a single point, if we were just to kind of look here, let me get a different color here. If we were to look here, we could count that this blue, for example, has 1, 2, 3, 4 in the same time that this only has 2 peaks. So this blue has a higher frequency, but if you notice, it has a smaller wavelength associated with it. And we'll talk more about these relationships in class. So you might remember from your middle school science classes this little acronym or mnemonic device, ROY, G, BIV, okay? So red, orange, yellow, green, blue, indigo, and violet. And so you guys, again, do need to memorize this. I'm sorry, I feel like there is a ton of memorization going on here. But what you definitely need to remember is that red has the longest wavelength and violet has the shortest wavelength. So here's the picture of the electromagnetic spectrum that I promised you. In the middle, you guys can see there's visible light. Let's look at our units. So in this case, we're measuring our wavelength. So you can see that our wavelength is getting bigger here and the values are smaller up here. And so gamma rays have a really small wavelength, which means they have a really high frequency associated with them. And then there's X-rays, then there's UV light, then there's our visible light, our infrared. And so like this is like what you might see like with your TV remote control or something like that, or I feel like in spy shows you're always seeing like those red lines that people are stepping over. Then here's microwaves, so the things that cook our food, and then radio waves. So if for those of you guys that remember, there's these things called radios. You can turn the station and listen to music. I know you all are on iTunes now, but this is what us old people used to listen to. So here we're talking a little bit more about the relationship between these variables. Again, a short wavelength has a high frequency. And remember how we just saw in the last slide that gamma rays have a short wavelength? So that means they have that high frequency. That also means that they have a high energy associated with them. And hopefully that kind of makes sense because if you know, gamma rays can cause cancer. They're really damaging to you, just like if you've ever gotten an X-ray. X-rays are right next to gamma rays. They'll put that little tarp, that little lead thing over you so you're like not damaging your organs and stuff like that. So high energy is associated with a short wavelength. On the other hand, radio waves are going through the air all the time. So those guys have a really long wavelength. So that means they have a low frequency and then therefore they have a low energy. I just checked the time on this video and it looks like we're just at about 9 minutes, so I just want to go ahead and wrap this up. So a couple of key points here is that you should know that visible light is part of this electromagnetic spectrum. You should know that the speed of light travels at that 3.00 times 10 to the 8th meters per second. You should also remember that formula. Another way you'll see the formula written in class is C equals the wavelength times the frequency. And we didn't really talk about this. I feel like this is like a little A, it looks like a little A, and this looks like a little V, so depending on the worksheet, this is how they should look, but they might look a little different on worksheets. Also, don't forget the parts of a wave, as well as have an idea about the electromagnetic spectrum, about which types of electromagnetic radiation have high energy and which have low. Thanks. Have a great night.